Well, welcome to the myth of the times 10 programmer. I'm going to talk a little bit today about the programmer productivity ranges, and some of the things that we've learned that challenge the myth of that super times 10 programmer. The history of programmer productivity and measurement goes back a long way. It started in the 1960s, and measurements of programmer productivity ranges have typically been around 10 to 1. They've ranged from 5 to 1 to 28 to 1, but consistently, the researchers have found wide ranges of productivity among professional programmers. This has been replicated countless times, and if you want a really good summary, check out Steve McConnell. Why does the productivity range really matter? Well, productivity is important. It's part of getting the work done. It can affect hiring. How do you hire the best programmers? What about evaluating programmer effectiveness or promoting or retaining those high-performing programmers? You have to know the productivity for planning. It matters a lot. Now, what we wanted to know was what factors are there? Educational factors, experience? Is it something about the individual? What accounts for the range in this performance? We wanted to see if our data replicate the scale of these performance ranges we've seen before. Do these ranges still exist? And what are the practical effects of these differences? We looked at this as part of the SCOPE research project at the Software Engineering Institute. We were looking at productivity rates. How does the productivity vary among the different programmers? So to do that, we wanted to look at some actual data that we collected during the personal software process course that we taught for about 10 years. Everyone who took this course did the same 10 programs, or at least they programmed to the same requirements. While they took this course, they recorded a lot of data. They recorded with stopwatch precision the time that they spent on the program. They used forms, they recorded in logs, they recorded their effort, they recorded the size of the programs and the defects. The programs typically took about an afternoon to write, but they varied in size at least somewhat. So with this sort of information, we have 10 repeated measures for each of the students. Now, what really sets this apart is the scale of the data. We had, over the first 10 years of this course, over 3,000 different developers go through this course. Now, at least over 30,000 actually completed. Over 3 million lines of code, over 100,000 hours of programming. We also were able to collect a lot of demographic information on the participants. This included things like their years of experience, their education level. We also had a lot of information on the different languages that they were using. And we decided that we were going to constrain this particular study and look only at those who worked in C programming language. We also focused only on the programming effort. That is, how long did it take to write the programs? There are other things we can look at, and I can talk a little bit about those offline. For the analysis, we were applying what are known as causal search techniques. This is a completely different subject. I don't want to go into it, but I highly recommend things like the work of Judea Pearl if you'd like a little more information. For the detailed analysis, we were using things like linear hierarchical models and structural equation models for SEM to measure the effect of the size and to quantify the variation. Now, the interesting thing was when we were looking at this data, the causal search techniques would allow us to identify the arrow of causality where there were relationships. So it would look for not only correlational relationships, but could infer from certain structural patterns the direction of cause. Interestingly, not very surprisingly, we found primarily the causal things were how big was the program. This could be either how big was the particular implementation or the size in a more abstract sense of how big was the assignment, how big were the requirements. We found that the defects were related primarily to programming effort, and the programming effort was largely a matter of the requirement size. All of these depended on the student, however. So the student was a common factor in each of these. So there was something about the student that did vary very clearly. But we found another thing. The amount of variation within each programmer was surprisingly strong. That is, not only was there a difference between the different programmers that would affect their size, their defect, and their effort, but each individual programmer had a large variation in his or her performance. So we decided we were going to take a closer look at this. This chart is a histogram of the total effort each student put into the entire course. On vertical, along the axis, we see the number of students who took a certain amount of total effort. This is relative effort, I should say. We normalized the effort to the average. So the average in this case is going to be 1. And if you look at the far right, we do see that there are a number of students who took somewhere around 3.5 times the average. And there were a few who took somewhat less than half the average. So if you look at this, you might have some justification for that times 10 factor. But we'll also notice that there are really only a few outliers out here, and the real range was really somewhat more narrow. Moreover, if we see the top 5% and the bottom 5%, their relative efforts weren't that different. We get about a factor of 5 from the best 5% to the weakest 5%. And to get beyond that factor of 5, you really have to look at just at the outliers. So this raises some additional questions. We'll look at this a little more carefully. We plotted the relative effort for each of the 10 programs. So this is a quartile chart for each of the 10 programs for relative effort. So again, the relative effort, the average, the mean is going to be 1. And we found a very wide range between the maximum and the minimum times for each program. We can see that the ratio of the minimum to maximum range from about 20 to 1 to 50 to 1 for each of these exercises. Now, that alone was pretty surprising because this range is much, much bigger than we were seeing for the overall 10 assignments. That means there's a lot more variation going on program by program. But we also saw the interquartile range, that is the middle 50% of students, were actually in a very tight range. They were typically in a range of 2 to 3 in total performance effort for the effort. So you've got this dichotomy. We have a wide variation at the extremes, but most of them are bunched up in a fairly narrow performance range. So this raised even more questions. So what I did here was I developed what we call a caterpillar plot. And the caterpillar plot is very useful for showing the what is called the within and the between variation. The between variation is shown in this blue line with the central tendency. So in this chart, as we move along the horizontal axis, we can see the rank of the student. That is, we took their effort and ranked it from 1 to 494. Where did they finish? Their median score is along that blue line in the middle. So that blue line shows a nice linear trend between 0 and the total population of 494. What is interesting is now we can also look at the vertical. The vertical axis at each point shows the range of performance. I didn't show all of the different performances, but what this shows, if we pick a particular point, as in this one box, we can see the 90% confidence interval on that student's average performance, on that student's median performance. We get this by taking the total range of ranks. For each assignment, they had a rank, 1 through 495, and we plotted those along the vertical axis. And what you can see here is for the top 5% of the programmers, that is 1 through about 25, you will have a rank that ranged from 1 to a little over 100. So the top 5% of the programmers you could generally place within the top quintile or the top 20% of overall performance. That's a pretty big range. And we saw something similar at the other extreme. The weakest performers, 5% of the weakest performers generally finished in the bottom quintile, but they were a little more variable. What about the middle performers? We looked here at about the middle 50% of performers, and you can see that along the vertical axis, there's a huge range. Your typical programmer somewhere in this middle would have a range of somewhere about 250. Now, let's be clear about this. This range of 250 is our best estimate of their median performance, of their median rank. So after 10 exercises, most of these programmers, we can estimate their rank only to within about half the total population. So what we're seeing here is the individual programmers have an enormous variability from one exercise to the next. So if I come back to this slide here, we have all of these performances. We have this very consistent interquartile range. We have these very consistent lines along the quartiles, but it's different programmers every time. So the individual programmers are behaving very differently from one assignment to the next. Now, to make this a little more quantitative, a little more in rational numbers, there's a concept called the intracluster correlation coefficient. And we measured that to be about 0.6. That means that 60% of the variation could be explained by identifying the programmer, but about 40% of the total variation was still that noise term within the individual programmer. So almost half of the variation that we were seeing in the productivity was just noise within one assignment to the next of a programmer's performance. Now, this is kind of important because this variation, to my knowledge, had not been previously reported. And that could have a lot of effects on how you do these measures. Again, go back to the quartiles. If you are measuring performance and you measure any one of these programs, you're going to get these wildly fluctuating numbers. Might be 20 to 1, it might be 50 to 1. And if you say, well, this is a measure of the real difference among programmers, you would be wrong, because what you've actually measured is you've conflated the difference within the programmer with the differences between programmers. A lot of this huge variation is, in fact, just random noise. So this wide minimum max range remains, but most of the developers, almost all of them, fall within a much narrower range, maybe ×5 productivity. And most of your normal programmers, half to 2/3, fall within a range of about 2 to 3. So there's some real differences among the programmers, but they aren't nearly as vast as we had supposed. And this really does, again, emphasize the point that if you just take a single measure and you don't account for this type of variation, you're going to overestimate the effect of the programmer, the individual programmer, on this productivity variation. It also says that you can get essentially whatever min-max ratio you want just by varying size or taking different samples. We found among these 10 programs a huge variation in the min-max using exactly the same programmers. What are some of the implications for this? Well, if I'm in industry, I've got to realize that this min-max ratio doesn't really tell me what it sounds like, because what we're really doing is we're measuring the outliers, not the main effects. Also, the numbers tell me that it's going to be really hard to get enough of those top programmers, those super programmers, to really affect the performance of a large program. Most of your programmers are going to be in that vast middle, and it turns out that vast middle are going to be fairly consistent performers within a fairly narrow range. That's where most of the programmers are, so I'd suggest you really have to find better ways to use those programmers. Why were some of these programs taking so long? Normally it was because the programmers were getting stuck somewhere. They misinterpreted a requirement. They had some kind of bug that they just couldn't see. So the real power of the outliers wasn't to identify weak programmers, it was to go and give them help when they needed it. Also, if you were trying to improve productivity any number of ways, if you're trying to improve the environment, if you're trying to give them better tools, if you're trying to provide training, don't rely on just short-term numbers, because in the short term, this high variation is going to swamp every other effect. This variation is huge, and I can't emphasize that enough. And finally, I want for the industry to recognize, don't focus just on productivity. Other factors are going to matter. And the other factors are often things that you can control. You can provide good environments. You can provide nice, quiet work environments. You can insist on having good designs. You can train for designing. You can provide better tooling. You can emphasize the importance of peer reviews and quality over just being fast. And it turns out most of these other factors are much more trainable and much more controllable. So these are your real leverage points. Don't just focus on productivity in the short term. Think about this from a broader, long-term perspective, and you're probably going to have better performance overall from your entire development chain, and you're certainly going to have happier programmers. For researchers, well, one of the things that I'll point out here is the scale of individual task variation has been under our noses for 50 years, and yet there is almost no literature on the subject. To my knowledge, this is the first time it's really been looked at carefully. It gets to some very basic questions of validity. No one thought to question the reliability of the measurement. How reliable are those measures? Well, that depends on the individual variability. What about the predictive variability? If you have these sorts of measures, how much do they predict the next one? Well, if you have a lot of measures, we showed that the central tendencies were pretty consistent. But point by point, they're just all over the place. Now, what are we actually trying to measure? What does this mean for applications of data mining or machine learning? Certainly these issues of construct validity, variability, these can have a lot of implications when you're looking at the observational, historic data, what types of algorithms are going to be most reliable for machine learning. You've got to think about these issues very carefully. And you also want to think about how this data is being generated, how this data is going to be recorded. And for these purposes, I really do want to give you the opportunity to look at this data yourself. So I've attached here a link to the personal software process data on the IEEE data port.